So, you now understood that how do you use it for 1 bit equality comparator. Okay. So, we are going to there will be other uses of 1, in particular uses like addition. Okay. So, those kind of functionality is also available, right. So, we will go into computer arithmetic in more details, but let me give you a very quick intro, right, because we already have the truth table and we all know how to add binary numbers, right, just 1 bit binary numbers. You can also interpret this particular x and y whenever we are getting the XOR value as a sum of x and y. So, I will tell you how. So, if you think x and y are two numbers, right, two 1 bit numbers. This was about the error checking. Let me erase this part. This was error checking. Let me come to the summation now, right. So, I will use it, I will use this part, I will use this part of the okay. So, the other use that we are going to have is building an adder, right. So, towards building a circuit for addition. Okay. So, coming back to the discussion, if you have these 2 bits, let us say A and B, right, and you want to add them, which is again going to be A plus B. So, there are two things, right. One is the sum, right. Typically, you have, if you add two numbers in the same decimal position, for example, units position, tenths position and so on, you have the corresponding addition value, and that addition can create a carry. So, all of you are aware of this carry concept. So, I will just quickly let us say if you add 3 and 5, right, this becomes 8, right? There is no carry forward, right. If you add, let us say 7 and 5, the sum is going to be 12, right. So, 2 is going to be remaining in the units place and 1 is going to be carried forward. Okay. So, in this jargon, right, in this wherever we are trying to design these adder circuits, typically this is known as the sum, right. So, 7 and 5 what remains in this location is called the sum, and what is carried forward is called the carry. Note that we are not talking about decimal numbers, we are typically talking about binary numbers here. So, the sum value could only be 0 or 1, the carry value could only be 0 and 1. Okay. So, I will erase this and give you an example in binary. So, if you look at the possibilities of A and B, this could be 0 0, 0 1, 1 0, 1 1, same as a truth table, right. If you add them individually, 0 plus 0 is 0, right, and no carry is actually produced, right. So, if you have another output called carry, that is not produced. 0 and 1 same thing, 0 plus 1 is 1 and no carry is produced. 1 plus 0 is same thing, it is 1 in the this place and sum, and the carry is 0. But if you look at 1 plus 1, 1 plus 1 is actually, even in binary it is like 2, right, and 2 is 1 0, right. So, 1 plus 1 in this least significant bit or the sum bit is going to be 0, right, and 1 is going to be a carry forward, right, or carry that is going to be generated from the addition. So, this is often called half adder. Okay. We can use this XOR circuit to add these two numbers, right, and you may have multiple bits, then we are going to study about full adders and so on. But here if you look at the very simple interpretation or another interpretation of XOR as a half adder, we have looked into comparisons or error checks and so on, right. This is as a half adder. Okay. So, let us now concentrate on the sum value. So, the sum value for 0 and 0 is 0, 0 and 1 is 1, 0 and 1 is 1, 1 and 1 is 0. Now, you can see this is exactly equal to the XOR function. Okay. So, you can see 0 0 0, here we have 0, 0 1 is 1, we have 1, 1 0 is 1, right, we have 1, and 1 1 is 0, we have 0. So, this bit often called the sum bit is an XOR, right. And if we talk about the carry bit, it is also very easy to understand. I mean, I think even without writing the truth table, right, when we had 0 0, right, I can even write it down. Maybe I will use an eraser here and write about the carry, right. So, the carry is going to be, if you have 0 and 0, as you can see, the carry is going to be 0, right. If you have 0 and 1, the carry is going to be again 0. If you have 1 and 0, the carry is again going to be 0. If you have 1 and 1, the carry is going to be 1, right. So, this is basically your carry bit. And can you guess what is going to be this function? I mean, this is very easy, just by looking at the truth table, or even logically hearing this thing, right. So, it is always 0 if any one of the inputs is 0. You can very easily see, only when both of A and B is going to be 1, only in that case the carry bit is going to be 1. Okay. So, by definition, the carry bit is going to be an AND function. Okay. So, this is another interpretation of this XOR functionality, that it can be used to add 2 bits. Okay. So, the addition or the sum bit is represented by the XOR function, the carry bit is going to be represented by the AND function. Okay. And you can think more about it. For example, the initial thing that I told you in the last slide here, right. So, if you want to, for example, implement this kind of comparators, right, x equal to y, right, and x not equal to y. So, you want to output different things. X and y could be 1 bit, x and y could be multiple bits, x and y could be 2 bits, 3 bits also. Okay. So, here you need to think about how do you compare 2 n bit numbers where n is not 1, n could be greater than 1. Okay. So, this is one example. Here I have taken 3 or 4 bits, right. So, this is A, which is a 4 bit number, same for B, B is also going to be a 4 bit number, and let us say 11 and 9, right. 11 in binary, 11 in decimal is represented by 1011 in binary, whereas 9 is 1001, right. Just a quick revision, if you are not able to quickly do it, you can you have to practice, right. So, you can always think of this as the first significant bit, right. This represents 8 because 1000 is 8, 1 followed by 3 zeros, then 1 followed by 10 is typically is actually 2, right, and 11 means 3. So, 8 plus 3 is 11, right. Similarly, here 1 in this position means you have 8 plus something, then there is only a single 1, right. So, 8 plus 1 is 9. So, this is 9. So, you need to kind of practice all these various things, right. So, suppose I call if you ask you to do for 13, okay. So, you know 8 plus 5 is 13, right. So, 8 is there and 5 is again 4 plus 1, right. So, 4 plus 1 is 4 is 1 followed by 2 zeros, instead of 2 zeros you have one more 1, right. So, 8 plus 4 plus 1, okay, that is 13. You can always do it in the formal way, right. So, the formal way is basically look at the bit positions. This is the 0th position, I will use the other color, and this is the 0th position, this is the first position, second position, third position. So, 1 into 2 to the power 0 plus 0 into 2 to the power 1 plus 1 into 2 to the power 2 plus 1 into 2 to the power 3. So, this is equal to 1 plus 0 plus 4 plus 8 equal to 13. Okay. So, you have to kind of be in a habit of converting decimals to binary and vice versa. Okay. At least like for at least 6 digits or 5 digits, at least 5 digits you should be able to do just in your just mentally, right. This is very useful once you start designing some circuits. All these things is going to be kind of really helpful. Okay. So, in this particular example we want to output A not equal to B. So, if A is not equal to B, we can output 1, right, or if A is equal to B, we are not going to output 1, we are going to output 0. So, one way is to do this bitwise comparison, right. So, I can just do a bitwise comparison, and if A and B are both equal, what is going to happen? They are going to output a 0, right, and if they are unequal, they are going to output a 1, right. So, this is that thing, right. So, you have this 8 bits as an input, you take the first bit of the first number and the first bit of the second number, you compare them. So, this is a comparison that takes place, this is another comparison that takes place, another comparison that takes place, another comparison that takes place. Now, if even a single comparison fails, then the entire comparison will fail, right. So, if you have output here, right. So, if your numbers are equal, this is going to be 0, right. If they are unequal, so this is 0 for equality and 1 for if they are unequal. Okay. So, we are using the series of OR gates, right, where does not matter even if 1 is a 1, right, in any of these 4 lines you have this 4 lines. In any of these 4 lines, if you have a single 1 that is present, does not matter what about the rest of them, this 1 is going to percolate to this particular gate, right. So, suppose you have 0 0, fine, this is going to come up with a 0, but at least one of them has to be 1 for the last 2 bits, right. So, this has to kind of, let us say this is 1, let us say this is 0, this will become 1, right, and then this is going to become 1. Okay. So, if A is not equal to B, you are going to get a 1, okay. Otherwise, you will get a 0, which basically means that they are equal, okay. Because if they are equal, all of them are going to be 0, and here you are trying to do an inequality testing if they are A not equal to B. Okay. So, this is going to be a very useful circuit for doing such comparisons. Okay. This is and you can come up with your own circuit, that is what I would recommend. For example, if you want to do something like you want to do A greater than equal to B, let us say this is output is, this is a problem that you can try out. So, output is going to be let us say 0, okay, and if A is lesser than B, the output is going to be 1, okay. And let us stick to this let us say 4 inputs, right. So, the way I would kind of ask you to do is that you have to simply write the truth table. Do not worry too much about the final circuit, because final circuit you cannot find out directly, right. What I told you in the very first few lectures is that given the logical problem, you need to find out the truth table or the functional specification, but functional specification you do not directly know, you need to find out the function, right, either in some sum of products form or some product of some form and minimize them, that is a different thing. but given the logical problem you need to find out the truth table. So, how do you proceed with the truth table? Let us say A and B are, like, for simplicity I can now take 2-bit numbers, right. So, you have A1 A0, this is A, B1 B0, this is B, and then there is an output. Okay. So, now you need to fill up this table. Okay, I will do a little bit and then you can carry forward the rest. So, let us see, right, whenever you get this kind of problems you have to write up the truth table. So, it is a 4 inputs together are there, right. There are 2 numbers, each number is a 2-bit long thing, right. So, you are going to have starting from, you are going to have 16 entries first of all, from 0 0 0 0 to 1 1 1 1. So, you can write all these entries like this 0 0 0 1 0 0 1 0, this is 2, this is 3, right, this is 4, right, and this is nothing but this entire chunk from this part to this part, right, is going to be repeated, just with 1 0 is going to be flipped to 1, right. So, now you can see I can just change the color, you can understand it better. So, see 0 0, then you have 0 1, then have your 1 0 and then you have 1 1. Okay. So, this entire thing is the same thing, right, for B1 and B0, just that A0 is going to be 1. Okay. So, next so and A1 is going to be 0. Okay. So, next what you do is A0, B1, B0, these 3 things are again going to be copied, only thing is that this is going to be flipped to 1 now. Okay. You basically copy paste the entire block, right. So, this entire block, right, this entire block is going to be copy pasted here, just with an exception of A1 is going to be 1 now instead of 0. Okay. So, you should be now practicing how to write this truth tables and create Boolean expressions out of them, try to simplify them and so on, right. In the context of this problem, here you need to determine the output. So, we said that if A is greater than equal to B, then it is going to be 0. So, if you look at these numbers A1 A0, B1 B0, they are definitely equal. So, the output is going to be what? The output is going to be 0. Then look at the next thing, right. So, in this case A is 0, but B is 1, 0 1 means 1. Okay. So, 1 is greater than 0, so B is greater than A. So, in this case the output is going to be 1. Okay. So, similarly here B is 2, A is 0, output is going to be 1, in this case B is 3, output is going to be 1, right. In this case A is greater than B, because A is 1, B is 0. Okay. So, the output is going to be 0. The next case A is 1, but B is also 1, right. If A and B are equal, we are going to put 0. Next case is A is 1, but B is 2. So, this is going to be B greater than A. So, 1. In the next case B is 3, but A is 1. Okay. If A is 1, so all of this numbers, so in this particular thing, right. So, this is 0 1 0 1 0 1 0 1, right. So, all of them, so are, so this is A is 0. Okay. Here A is equal to 1, because 0 1 0 1 0 1 0 1. Okay. So, after that you will basically get 1 0 and so on. In that case A is going to be 2, but we are just trying to do it till here. So, 0 1 means A is 1, here B is becoming 3. So, 3 is greater than 1. So, this is going to be 1, right. So, you are going to have more entries. So, some of the mean terms that you can definitely pick up is, let us say, so what are the mean terms here that are going to be picked up if we are trying to build a sum of products expression. So, this is going to be picked up because this is associated with 1. This is going to be picked up because this is associated with a 1. this is going to be picked up because this is associated with a 1, right. This is going to be picked up because this is associated with a 1, and this is also going to be picked up, this is associated with a 1. You can write the mean terms. For the first mean term, let us say is A1 bar, A0 bar, B1, B0, right, and then you have to write a plus because you are trying to make a sum of products expression, because these are the mean terms that you are planning to, you are picking up. The next term is this, which is again A1 bar, A0 bar, followed by B1. So, the first one is I think B1 bar B0, this one is B1 B0 bar, right. Yeah. So, the last one is here A1 bar, A0 bar, B1 B0. So, these are the first three. If you take this one, this will be plus again A 1 bar, A0 because this is 1, then B1 B0 bar, then the next one can be A1 bar A0, right, and followed by B1 B0. So, these are the 5 mean terms that I have written, but once you complete the table there could be more mean terms, right, and then you can try out things like simplifying the expression further. For example, I am just going to give you say you want to club this particular term, right, and this particular term. So, you can very easily see that B1 bar and B1, these are going to cancel out if you take A1 bar, A0 bar and B0 common, right. So, I mean this is the general way to approach this kind of problems. Do not worry about how complex the circuit looks like right now, because first you need to kind of be confident to design the circuit or even implement the truth table even in an unoptimized way, given the logical problem that you have to solve. Okay. Welcome to Decoder Lit.